Good day to everyone from around the world, and welcome to what I hope will be and expect to be a pretty fascinating and interesting discussion of geospatial analysis in the age of AI and how we can apply this to conservation in meaningful ways and ensure that we are capitalizing and utilizing some really remarkable breakthroughs in a manner that will help us protect this planet that we all love. I'm Paul Bunje. I am the president and co-founder at Conservation X Labs. Very pleased to be co-hosting this webinar today with Karl Burkart from the Nature Data Lab at One Earth, and really excited that we have joining us Dr. Alemohammad from Clark University to share some really great insights. Very briefly, the Nature Data Lab and Conservation X Labs wanted to start putting together an opportunity, a forum, where it is that we could start to dive into some of the new tools and technologies that are starting to transform our ability to measure and conserve the planet at scale. And in particular, with the advent of artificial intelligence tools and how they have aided and abetted the types of remote sensing and big data that have existed for a number of years now, we're starting to see some real breakthroughs and some real opportunities to transform our ability for assessing and understanding nature at scale. But of course, this means for a lot of us, a lot of confusing new terms, a lot of confusing new techniques, a lot of new science. And we recognize through a number of different conversations and meetings, including one that a small group of folks joined in Washington, D.C. earlier this year, focused on conservation technology and how it is that we can actually expand this field. We recognize that there's really so much out there that it would be wise and helpful probably for a lot of people, from practitioners and scientists to funders and regulators alike, to have a forum where we might be able to discuss and understand the details behind some of these new tools and techniques. I know a lot of you are probably approached regularly with some new cool thing. Hey, use this map. And the question is, okay, why this? Why not something else? Right? Where are we? So that's kind of the point of these webinars, and we're hoping this is the first one. We're really hoping that this turns into a really exciting opportunity to dive into other new tools and technologies and techniques that are transforming our ability to protect this planet. So if you have ideas as well, please do reach out to us, because we're keen to host other experts that are able to help demystify and clarify the different new tools in a specific area that there might be in today. And of course, today what we're really looking at is geospatial analysis and how it is that new tools and projects like Land Cover Breakthrough, that I know Hamed has been working on quite a bit, relate to other new approaches and how it is that they might be utilized. Before I turn it over to Karl to introduce our speaker today, just want to say a brief thank you to everyone for joining us. We at Conservation X Labs, we have a bold mission to prevent the sixth mass extinction, and we recognize that what that means is meeting the speed and scale of the biodiversity crisis requires us to do things fundamentally differently and in a revolutionary way, rather than the sort of evolutionary or linear approaches that have long been taken. And that means a couple of things to us. Number one, how do we capitalize and utilize new technologies like AI in a way that actually can reach the scale of the crisis that we're looking at? And two, how is it that we help transform the community, bring in more solvers, bring in more folks into conservation, and really utilize the power of networks such as all of you today that will help us actually achieve these bold goals that we know are necessary if we are going to maintain this thriving, beautiful planet upon which we live. I want to turn it over to my good friend Karl Burkart now from the Nature Data Lab at One Earth.
Yes, thank you, Paul, so much. I'm really excited. This kind of came together quickly, and CXL is just always pioneering so many great convenings and research. So I feel like it's a special opportunity for all of us. And it should be, as Paul mentioned, the first in a series. This is that we're co-convening with Nature Data Lab. So the Nature Data Lab is a brand new thing which I'm leading, which is housed at One Earth Philanthropy, and it's dedicated solely to accelerating the nature positive transition through applied science. So that's its mission. And Today, I'm super excited to introduce you all to Hamed. I first met Hamed, I think, nearly 10 years ago when I was starting to build the science and technology program at the Leonardo DiCaprio Foundation. And Hamed was kind enough to give me a lot of time and kind of gave me a crash course in geospatial analytics as the new director at the time of Radiant Earth Foundation. And his research prior was really interesting. Really systems research, looking at processes linking water, carbon, and the energy cycles together. And central to those conversations were back then, was the need to improve the quality of land cover maps in order to support the research around the way these systems work. And then since that time, Hamed has gone on to become the director of the Center for Geospatial Analytics at Clark University. And you probably heard his name. He has led some of the most advanced research efforts on remote sensing, earth science, AI foundation models, including co-authoring an AI foundation model. And it's such a treat to hear from him today, as we are beset, as Paul mentioned, with this barrage of new announcements in the space. And so Hamed's going to help us figure out the lay of the land today. And I do want to say, at any point in which you have a question that's something he says triggers a question you'd like to know more about, just type it in the chat, and we've got someone, thankfully, at CXL who's like monitoring all those questions. So with that, hand it over to Hamed, and yeah, enjoy.
Hello, everyone, and thank you to Paul and Karl for the organization of this session, and also for the invitation. I'm excited to be part of this conversation and share some of my thoughts about where we are in the age of AI, about land cover mapping, and what is next, where we can move forward basically to advance the field. Just one quick second. For some reason, my Microsoft PowerPoint crashed for a second, so I'm going to load the presentation. Okay, so I'm going to talk about, as the title of the talk says, putting nature on the map. So we all care about mapping natural land, and we want to see how can we do this in the age of AI. And to reflect on that, I'm going to go over some of the history here. So I will start with what is the need, why we need to do this mapping, what is the impact of having such a map. Some of the key terminologies and concepts, because we have heard all of these jargons and the keyboards, so it would be good to basically have a level ground in terms of what do each of these words mean. I'll talk a little bit about the evolving landscape of land cover mapping, how we have done it in the 70s and the 80s when the Earth observation satellites became available, and then where are we now with the age of AI and deep learning, and what are the opportunities and challenges with the rising of Earth observation foundation models. And then some final thoughts about what is needed to go after a global ecosystem map, basically. So this might be principles for many of you, but I'm going to review why we need to have a reliable global land cover map. You can think about the need for climate and biodiversity action. We need a high quality map. And I want to mention this, that quality means different to different people. So I'm using it as a very generic term here, but what is accuracy, what is quality? It depends on the user. But I think all the users, no matter what is their metric, they require a better and accurate and basically higher quality map. And this is important for many environmental and decision-making factors. Thinking about like forests act as a major carbon sink. So being able to, with high accuracy, map them and monitor them regularly, it is of essential, basically, importance. Being able to inform global targets and policies. Think about, for example, the 30 by 30 initiative and the national pledges that the countries and the governments are putting in. Those policymakers rely on these data sets to be able to first make a pledge and also then monitor the progress toward those. So having a global, again, consistent, reliable map of natural class is important. To be able to support ecosystem services and livelihoods. I mean, wetlands, for example, hold about 20% of the planet's organic carbon, despite just covering about 1% of the Earth's surface. So this is a significantly important class. So to be able to monitor them, to be able to see their extent and also their change over time and anthropogenic impacts on them, we need a reliable land cover map. And also to be able to guide conservation investment and corporate action. There's a growing trend, as many of you know, in terms of corporate responsibility and initiatives that they are putting into protecting natural land and also being able to report on their progress. So it is important to know where and how those investments can be impactful and where resources needs to be deployed, basically. All of these underline a need for reliable global land cover maps. And we know there are many of those maps out there. So just some reflections of what are those high-level limitations of the current land cover maps, particularly as it comes to mapping natural classes, because that's where I think many of these important factors comes in, and those underlying basically needs are focused on. You can think about one of the issues being these maps usually have broad classes that hide the heterogeneity and within class variability. A typical word in land cover maps is forest. But if you go around the board and ask ecologists in different continents, what is a forest, they will give you very different definitions, depending on the basically sparsity or the density of the trees, the type of the trees, and so on. So having those local nuances is important, which many of these maps unfortunately don't have. So it is important to bring that into the place. There's also, speaking of the heterogeneity, this is the one-size-fits-all model that doesn't work, basically. We can still have, in my opinion, a global map of the same land cover classes, but have hierarchical, basically, land cover definitions that then define what is a forest in a regional context that is relevant to the people. And then the policymaker, the investor in the local region can connect with that and make decisions. The accuracy of these maps, again, in generic terms, is limited by the resolution. So as you know, in the satellite world, we have some very high spatial resolution satellite data commercially accessible, like each pixel being 30 centimeter. And then we have open data sets that are available from more government agencies that are like 10-meter resolution in terms of the pixel size. Those high resolution ones can potentially provide a better quality map if you have the right data, the right model and everything. But because many of the models are fit at the 10-meter open data sets, they have basically limitations in terms of what can they see at the 10-meter resolution. Sorry. There's also some misclassifications that are systematic, particularly because these models are confused about natural classes. You can think about like a semi-arid region, a shrubland and a grassland and a bare ground will have a lot of interconnectivity, and the seasonality will be very similar. So being able to build a model that can detect those nuances and separate them out so we can have a right classification of, again, certain natural classes is important. And there has been improvements. That doesn't mean we haven't improved in these classifications, but these are existing, basically, challenges. And last but not least, these models rely on what they see in the image. They look at the vegetation, for example, or the built-up class. They don't necessarily look at the impact of humans on the ecosystem, basically. And they cannot basically show anything about the intensity of those. So being able to build models that actually connect to the human interaction would be the next level of, I think, land cover mapping to look at the natural classes and provide better data, again, for decision making. I'm going to show a few examples of where these models can be wrong. This is a recent study that actually looked at several global land cover maps. Here we are looking at the 4 of them, the IGBP, the CGLS, the UMD, and the ESA one. And they use an existing data set of mining sites, which were basically ground reference, and they know there is a mining site at that year in this place. And then look at what do those land cover maps classify this mining site. And mining is an anthropogenic surface, like it is a changed surface, it is not natural. And we see that on average between 56 to 77% of those mining sites are actually classified as natural in that land cover map. They can be a mix of things like evergreen forest, from close shrubs, woody savannas, and so on, depending on the land cover. You see the subclasses here. But the green bars basically is showing that that site, based on this data set that has mining, was classified as a natural land, and a smaller percentage, about 30 to 40%, classified them as anthropogenic. Between the two data sets, this is different because they look at different mining sites, and different land cover products have a different range. But on average, again, 56 to 77% of the mining sites are classified as natural land. So that's that's a red flag for anyone who wants to use these global products for classifying and understanding natural land. Another example is another paper from last year that looked at the basically consistency or inconsistency between different land cover products to see how they classify cropland. Again, another class that is not natural, but we know it has significant basically land cover change that goes from natural to agriculture and cropland because of the pressure on food production and food security. They looked at 8 countries in Africa, which is one of the regions that is going through significant change because of the expansion of agricultural sector. And what you're seeing here, a lot of bars, but I'm going to simplify it for you. Each color basically shows a different land cover product. So 11 colors for each of the products. On the x-axis, you see the countries, the 8 countries that the study was conducted. And on the vertical, you see 4 different metrics in terms of accuracy. And as you see, there's significant variability in terms of the accuracy of the model in detecting cropland, which the team of the authors in this paper used an expert annotated data set independent of all of the land cover products to benchmark these against those reference points. And they only looked at cropland, no cropland class in this case. But you see significant variability across regions, some models performing well in one region versus the other one, and some models basically consistently being low. So there is a mixed message here, and it's hard for a user to decide, okay, which one should I pick at this moment? And the point is, when it comes to the decision making, you don't necessarily have that benchmark data. So how you would go after making that decision is something that it needs more discussion and community development. This is also the same study showing how these different land cover maps are consistent or inconsistent spatially. When you see a red, it means all of them are saying there is no cropland here. So 0 of the 11 models says that. So that means agreement. When you see a blue, it means all of them are saying that is a cropland. So that is also agreement that 11 models say. When you see something in the yellowish, light greenish, it means the models are 50-50. So that means a significant portion of the countries that we're looking at, the models don't agree. And again, as a user, you have to find a way of understanding where things are and making a decision. So there is significant limitations into existing land cover products. And these can have significant consequences. You can have skewed assessment of the climate and biodiversity. You can think about, again, as we go back to my first slide about the usage of these maps, you can have a misguided priority if you're implementing a policy like EUDR or REDD+, how you would look at the land cover map over time and to see if there has been a change or a deforestation that would basically trigger a policy intervention. Corporate reporting and looking at measuring the impacts or footprint of a supply chain relies on many of these land cover maps that we know have issues. And of course, losing some of the vulnerable ecosystems to neglect, which is if we miss certain classes or miss the changes that has happened to them, it would then trigger action in the conservation, which would result in losing those vulnerable ecosystems. So that's the state of the land. That's where we are in terms of many of the land cover products. And then I'm going to give you a little bit history about what are these models, how do they make decisions, and where we are in the age of AI. But before doing that, let's do that a key concept, basically, introduction thing. We're going to use the term supervised learning, which is a term used a lot in nowadays machine learning. I would say a few decades ago, a lot in statistical learning. In these methods, you basically have a few examples of what you want to classify. Let's say you want to train a model that detects forest from water. You have some examples of those. You either annotate an image or you have referenced it on the ground, and you will show those examples to the model in the development stage or in the training stage. And the model is supervised, basically. You supervise it to learn what is a forest, what is a water. And that is a very classical machine learning methodology we have used for years. Many of these land cover products are supervised models. There's the new era of self-supervised learning, which in this case, you don't necessarily have any human labels or even model-generated labels, but you let the model learn from what we call the raw data to learn some representation, some inherent structure of the data. For example, you can pass a series of satellite imagery without any labels, just the raw multispectral data, for example, to a model, and then design architectures, design training strategies that the model can learn a representation of those and understand what is the distribution of these. And we'll see later on what is the value of this. But what is that? That is the concept of self-supervised learning. In this stage, you don't have any task or any label. Since 2021, the term foundation model has been coined, and this was a phenomenal paper by the group of authors from Stanford that published the idea of a foundation model. And what is that? It is basically an AI model that you train on a broad data set. So it should be representative, whatever is your distribution, it should be representative of that. And often this training is through self-supervised learning. So you don't define any label or any task for the model. And then after you do that training, the model can be adapted for different tasks or for different mappings in the case of remote sensing. But in the foundation model itself, you don't have a task. You just ask the model to learn from a huge amount of data set with a very huge architecture or the number of parameters and coefficients. And then you use that as a foundation. Similar to the concept that we have in construction, you build a foundation, and on top of that, you customize the building. The foundations might be very similar. But the point is that foundation is what helps you build the model, in this case, in the case of construction, the building and the structure quickly and easily, and then customize it as what is the utility of that building. After you have a foundation model, the term that you use to basically adjust the model is called fine-tuning. In fine-tuning, you basically show a few examples. Few means different in different use cases. It might be a few hundred, it might be a few thousand, to one of those foundation models or pre-trained models, as we call them. And at that moment, you will have a model that can make a decision on a specific task, whether it's a land cover mapping or something else. And then at the end, the concept of embeddings, which is basically that representation of the imagery in numerical space. So if you have some images like this figure, and you want to show them as a two-dimensional thing on a 2D space, you can train a model that understands those and maps those images to this vector space of embeddings. And that would be what you can use to make decisions later on. So embeddings are basically a transformed version of your image into a numerical space that is defined by your model. Historically, going back to the land cover basically mapping, the early days back in the 70s, it has been a lot of manual and supervised mapping using satellite images and this basically defining what we call decision trees. If certain phenomena, if certain threshold on this spectral band, this would be the land cover class. Gradually, in the early 2000s and so, the more advanced random forest and SVMs, these are the very early machine learning models, were built and adapted for remote sensing imagery, particularly the Landsat's time series of data, and also MODIS, which is another coarse resolution satellite from NASA. And land cover models have been generated using those sensors, using these models. Since then, we have products that have been consistently published using those. An example of them, for example, the IGPP land cover map, the very first ones that came out. And as I move through these few examples, you can look at the spatial patterns on the map and also the different taxonomy that they are using. So there is no consistent taxonomy in this case. And you see significant changes in parts of the world depending on how they define the taxonomy and how is the model making those decisions. GLC 2000 was another one that was based on Landsat 30-meter resolution global. And Globe Cover 2009. These are the early 2000 maps of the world. We have come way further from those days. There's a handful, maybe more of the deep learning-based AI models for land cover these days. They particularly use the basically convolutional neural network. I don't want to go to the technicality of those, but these are models that are not pixel-based. Before this era, everything was pixel-based. You would make a decision based on an individual pixel, their observation, and then assign a land cover class to them. In the cutting-edge AI world, we are using models that look at the neighborhoods, basically. They make a decision by looking at pixels around. And they have better performance overall. But still, we have inconsistency in those maps. I will show 3 examples here. This is a dynamic world from Google that is using Sentinel-2 data and mapping land cover globally using these classes that you see in the middle. So a consistent set of labels for built-up crops, trees, snow and ice, and so on. And I'm going to show you 2 other maps with the same color legend and similar insects from the 2 regions that we are looking in South Africa and in Brazil. And you can see the differences between these maps. This is the ESA world cover. I'm going to go back and forth. You see significant changes between these 2 at global level and at the basically small local level. And also this is the Esri/Impact Observatory land cover. Again, similar taxonomies in this study, they're mapped together, but we see significant changes and differences among them. And the point at this time is we have these maps, but they are inconsistent. So what is the issue where we can go next? And last but not least, the emerging foundation models for Earth observation. So this is now an era that we are building large-scale, broad models using the wealth and the history of all the satellite imagery that we have that can help us build land cover maps more accurately and move forward. I'm going to show you now an example that we worked in Kenya last year in terms of how we went from these global maps to a local scale map because the accuracies weren't good enough. And that would be a basically lesson learned of what we can do, an opportunity for future examples. So this is Murang'a County in Kenya. We're working with the Kenya Space Agency and the Department of Agriculture. This was a project joined with the Microsoft AI for Good team, our team at Clark University, and the Kenya Space Agency team. And as you see from these three land cover maps, the same dynamic world, ESA world cover, and Esri land cover, the same legend colors, you see significant differences between these three maps. And again, as a decision maker in the Department of Agriculture in a county, you are left with, okay, where are the croplands? Where should I deploy resources and how they're changing and impacting the natural class? And we know from the stakeholder on the ground, none of these maps are accurate actually. And the issue is how you can go to a next level and build a better map by learning from these global maps, because there are things that we can learn from them, but we need to adjust them locally. So we designed a problem space here, and we did an exercise that was, these maps are based on open source Sentinel-2 10-meter pixel resolution. Can we go to higher spatial resolution commercial data, learn something from that space, and then translate that to the open space? So we do what we call a teacher-student network in the machine learning world. In this case, you build a teacher model on the high-resolution imagery, like a teacher in a classroom. And that teacher teaches the student, which is the low-resolution or mid-resolution 10-meter resolution data, to make decisions on land cover classes. That's what the architecture of these is. They work hand in hand, and they learn from each other, basically. So we went in Kenya. We acquired some maxillary imagery in parts of the county. We didn't have access to the whole county, and that's part of the issue. So that's why we use it for guiding the student network, not necessarily replacing it. Then we generated high quality expert labels in the region. And that was engaging with the local experts who know the context, who understand it, and they can generate high quality data. We build a teacher model, and then the teacher model guides the student model to make decision on the county level map at a 10-meter resolution. And now you can see the fourth map, which is our map, the DATS map, in contrast to the other three that was existing global product. And you see significant differences and finer details coming out of that, which wasn't available in those maps. So visually, the experts validated this and made sense. We also did an independent validation, so just to have the numbers and have benchmark in terms of how good are these models are detecting crops and built-up, which were the two primary classes we were interested to solve for the stakeholders on the ground. And you see that the bottom row, all the accuracies closer to 1 is better in this case. They are all better than the existing land cover products that are out there. And the stakeholder is now using that in decision making. So this is one example of how we can go after enhancing and improving existing land cover products and customize them for the use case and application we want. Similar things can happen for a natural class or for a basically anthropogenic class, doesn't matter. It is about the methodology and the approach. So let's go back to the foundation models. I mean, this was an example that I showed what can we do with existing products. But now we have what I call the rise of Earth foundation models. What these models are, very broadly, but each of them have different nuances, is that we are feeding large amounts of multi-sensor, multimodal data into very complex architectures. These include multispectral data from satellites, synthetic aperture radar data from satellites, in some cases hyperspectral data, even sometimes multispectral from different sensors, like having a Sentinel-2 from the European Space Agency and the Landsat from NASA. And also in regional cases that we have airborne data, for example, in the US, we have the NAIP data, they are fused into one architecture. And then a model is trained on this raw data. Again, in the foundation level, there is a self-supervised learning. The model learns the self-representations, and I will share you some thoughts about how that happens. And then the model is used what they call in downstream tasks for forest monitoring, for land cover, for flood mapping, wildfire, and so on. At the end, these models are not the map. They are just another tool that help us do the mapping better. And you need to do this stage, which requires the expert involvement and the data, and we'll talk about that. But that is an era that we are living in now. And almost, I would say honestly, every week you see a new model. So there's a new architecture, a new set of data fit into that, and then a model is trained and released to the community. But one would ask, okay, why now? Why do we see this trend now, and why we didn't see it earlier or so on? Partly is because I think there are four drivers basically here. The data from those satellite sensors are becoming increasingly available on cloud platforms, so you can easily query them and access them. These models are data hungry. The model architectures in the AI world have advanced, and we have very better architectures and training strategies, so we can train these massive models. As I mentioned, the foundation model term was coined in 2021, so before that there wasn't anything similar to that. Of course, the compute power has enhanced. We have better access to cloud resources, and we can train these models. And I would say another driver is actually open science and collaboration. Many of these models, when you look at the list of developers and authors, there's multi-institutions coming together strategically, not just at the PI level, but strategically at the very high level, and working together, committing to work together to build these models. And that is what it requires. It requires a village to do these models. So how do these models learn? I wanted to put some light on just what is behind the scene of these models. So when you hear about them, you can relate to them and understand what does it mean actually. So I'm only showing 3 strategies that they're used to train these models. They are not inclusive. There are other ones, but these are the dominant ones that happens. One is called image masking, which is basically you get an image, you mask some pixels or some portions of that, and then you ask the model in the training phase to guess what is missing in the pixel. And through this exercise, iteratively, long iterations, the model learns those representations, those structures in the data. It is a very powerful methodology. And I would say easily 80% of the models in the Earth observation foundation model domain use image masking. Another strategy is contrastive learning, which you show 2 images to the model that say these are similar to each other, whether it's images from different days or images from different sensors. It's just different, basically, variations of the same image or the same location. And then you show a bunch of other images that are what we call negative to that. They are not similar. They're in contrast to this. They can be from different regions. They can be from different seasons and so on. Depends on your strategy for training. And through this exercise, again, the model learns to understand that the images that are closer to each other, how do they represent in that embedding space? And the ones that are further apart, how do they represent? Through this, again, iterative learning, the model learns that representation of the imagery, and then model architecture and weights are produced after that. And the last one is what we call diffusion, which is sometimes part of the same image masking strategy, but sometimes used differently, and that is generating from noise. So in this strategy, you take an image, you add noise to it, and then you remove the noise. Through this back and forth exercise, the model learns to go from noise to the image space. And in that way, again, learns a representation of your image in the embedding space, in that vector space. And through all of these 3 strategies that I mentioned, the model essentially learns the patterns, the seasons, the land cover types, the changes, without being explicitly basically told to do that. It just learns to what is in the data. And that is the key part. The data needs to be representative. Otherwise, the model doesn't learn those classes or those patterns. The advantages of this strategy is you will have a big model that is already trained, and it is what we call a backbone. You can use that as an off-the-shelf thing to customize it for your application. It is not done, it is not a map, but it is something that you can leverage and be a step ahead in your mapping. These strategies for training are very powerful as multimodal data integration strategies. So these models learn representations, and you can fuse in different modes, which wasn't the best, basically, I would say, capability of the traditional models in terms of mixing different modes. And of course, they can be helpful sometimes in detecting unknown patterns that we didn't think about. Let it be like an anomaly detection type of thing that we didn't have in our data, or we didn't think that can happen. Or it can be simply as like patterns, like a phenology type of thing, that again was embedded in the data, but we as humans hadn't thought about that. So they are very powerful in that sense. One thing I want to highlight, because I mentioned this a couple of times, is, so what are these models at the end? What can they do? You can think about them as a new toolbox that can help mapping, that can help monitoring. They are in some sense a flexible system you can apply to your problems, but they are not one-off maps. They are not ready products to use. They are yet another model, another architecture, another system that can help you build a good map and go into basically decision-making or policy-making. But they are very powerful. That is the point of these models, because they have learned from data, from large amounts of data. They are very powerful and they have learned a lot, but they are not yet the final answer to everything. We need to customize them, we need to use them, and we need to bring them to the context and work with the stakeholders. This is a list of just 6 of these models, the ones that I have seen. First of all, a combination of the latest one and the earlier ones. In terms of what they are, I'm going to share a little more about them, and also where they stand in terms of their size and their architecture and so on. Pre-3EO was one of the very first ones that I was involved with the NASA IBM consortium. It is built on multispectral data, so it doesn't fuse multi-sensors, but it is very much heavily focused on Landsat Sentinel harmonized data, or HLS, and it is multi-temporal, so it understands seasonality and you can feed in multiple data and then look at change and phenology patterns. It is fully open source and accessible to the community, both in terms of the model architecture, the weights, and the products. And it has 2 versions, a 300 million and a 600 million. Why the parameter size is important? Because it can give you a sense of what is the cost of building that model. You can build a linear relationship basically between those two. Tessera is a model that was released by the Cambridge University. It is multi-sensor, so it brings in multispectral and synthetic aperture radar. It is also multi-temporal. It is also open source, and it is about 1.4 billion parameters. So a different training strategy and adding multi-sensor. TerraMine was another multi-institution basically effort led by the IBM in Europe particularly. It is a multi-sensor, multi-temporal data, and it has a nice actually addition to that, which is what they call any-to-any model modality generation. So you can ask the model to generate the missing data. If your multispectral data is cloudy and missing, the SAR, the Sentinel-1 data, can fill in the gaps for you and generate that. So the model has learned those intermodality and intramodality changes and translations. Relatively lighter from Tessera, it has a 2 version basically, model 87 million and 300 million, again fully open source and accessible. Clay is another model that is also multi-sensor. It is not multi-temporal, it's focused on single snapshots. Another open source effort by the Clay Foundation, supported by many philanthropies and corporates, about 600 million. And as you see, there are similarities here and there are differences. I'm going to mention that. Dino version 3 is a recent model from Meta that wasn't actually trained for specifically remote sensing data. It is a generic vision model, computer vision model, but they have added remote sensing images in the training phase. So the model has seen many of those, and it is good at detecting some of the spatial patterns. It hasn't seen temporal data, so that's the missing piece. It hasn't seen the different modes of satellite data, like the hyperspectral and the Sentinel-1 synthetic aperture radar, but it is good at RGB images, basically. It is also open source, 7 billion. And then the latest one, AlphaEarth from Google, which is also multi-sensor. It has plugged in Sentinel-1 of the world, Sentinel-2 and Landsat, and also learn a lot of representations from climate data sets and biomass. The difference between AlphaEarth and the other models is at the embedding level, it looks at the individual pixels, and that is something I can get into more in the Q&A if someone was interested. But think about them as representations that are at pixel level rather than at the image level. It's about 1 billion parameters in terms of the architecture. This model, however, is closed in terms of the model itself, but Google has published the embeddings for all the pixels at the Earth for all the years that the Sentinel-2 data was available on Google Earth Engine. So you can access the embeddings and then fine-tune them for your use case, but you can access the model itself or reproduce the model as a use case, basically. I'm going to share one final basically use case and then go to some final thoughts of what is next. In this case, we're like, okay, a foundation model exists, the Pre-3 foundation model. We want to map mangrove forests as a critical coastal ecosystem. and their transitions to aquaculture ponds. We have a project at Clark CGA that we have done this for actually 10 years now, supported by the Moore Foundation. So using a very human-intensive pipeline and some statistical modeling, we have mapped at 15-meter spatial resolution coastal habitats in 17 tropical countries. So we have an existing large-scale labeled data, basically. And you can access that, by the way, on the aquaculture.earth website interactively and look at the maps. This is available. The challenge is that model is not extendable to other regions easily. It is not generalizable, basically. So that was where our hypothesis come in. Can we use the Prithvi EO Foundation model and extend this data set to other countries, to other regions? To do that, we took the Prithvi EO model, we fine-tuned it using the terminology that I mentioned with labels in Southeast Asia, and then validated this in Mexico, which is a very different ecosystem. The habitat is different. The ponds and the shapes and the phenology and everything is different. I'm going to quickly show this, and we want to leave some time for the Q&A. What you want to focus on here is basically these are different rows or different examples of that land cover mapping. But you want to compare these two columns. This is basically a reference label we are aiming to predict. This is what the Prithvi model is predicting. And it's very accurate in using different metrics that our stakeholders are interested in terms of the omission error and commission errors, and comparing to many other models, both the classical deep learning models and the supervised models. The foundation model strategy is working here, and it lets us basically do this mapping in regions that the model hasn't seen in the training stage. And that is the value of these foundation models. But the key was we had the right training data to fine-tune the model, and that was the key strategy here. So let's go to my final thoughts about what is then the opportunity with these models. So they provide, generally speaking, better accuracy and detail because they learn from diverse data. The overall performance of these models are better and they're richer when you're looking at very broad use cases. If you have a use case that is very nuanced, very small scale, and you have enough labeled data, usually you go with a supervised model still. But if you have something that you want to generalize to different ecosystems, to different regions, that's where the value of these models come in. They're usually faster in terms of running because you have already done a heavy lifting in the pre-training stage. So running inference is faster and quicker. And that's where the concept of few-shot learning comes in. So if you have enough data, you can fine-tune these models in a very small, light training stage in the fine-tuning, and the cost will be lower. They're good at understanding multimodal data, as I mentioned, and integrating those, particularly when there's missing data. They are much better at generalizing to regions that they haven't seen in the training data. The example of the mangrove was a good one for us, and we have seen this in other applications too. And they're good actually at discovering, again, new things, particularly if you want to find similar patterns. So if you throw some images at these models and look at their embeddings to see which ones are similar, those embeddings basically represent the context in the image. If you look at the image of a region and you see a lot of trees with a house, you would call that a forest with a building, right? If you look at the context, not necessarily individual pixels. That is what embeddings represent. And if you have multiple of those images, the models are very good, these foundation models, at finding those similar patterns and tell you about that. And if there is a change, that the trees are gone and it is now deforested, then it will be dissimilar to your forested image, and you can look at change at that moment. What they cannot do yet, and the challenges, I think they're still basically limited in fine classes, particularly distinguishing those fine-grained ecosystems and the differences between those individual classes. This is partly because of the training data bottleneck. You need those basically reliable training data for each of these fine classes, so the model is exposed to what are the nuances, what are the differences and similarities of those. Then those foundation models can be fine-tuned for those. But without those data, it is hard to imagine these models can detect those certain classes and be able to give basically a reliable prediction. Otherwise, it's just a guess. These models, it's hard to interpret them sometimes. There's a good field of interpretable AI, and they're advancing and new tools are coming up. But sometimes to put the human version of that model decision-making, it is still not possible. Why the model make a decision about this class, and how was the pipeline, basically. That is an area that is active research, but again, it's not yet there. Of course, computational resources can be a challenge. You as an individual cannot go and train a foundation model on your own without significant compute resources. So the foundation model generation is still in the hands of organizations and teams who have access to high compute resources, particularly a large number of GPUs. We need to be careful with data bias and coverage here, because if we say we have a foundation model that does X, Y, and Z, you need to go back and see what data was fed into the model in the pre-training stage. This is the classical quote about garbage in, garbage out. If you feed a lot of data that is noise or not representative, that model won't be reliable, and you can easily fine-tune them. So it is important, if you see a model, understand what was fed into the model in terms of the sampling, the strategies, and the data quality, basically. And of course, they're good at detecting what we call specific objects, distinct features, but they are hard at understanding compositions of things. For example, they can find a mining site, but having an understanding of a mixed class of a species or forest, it is still hard for them. Again, partly because in the input data, we haven't had enough representation of those, goes back to the data bias, and also not having enough training data or labeled data. So I think I've said this already, but this is what is needed to go next. Extensive training data if we want to do an ecosystem mapping, particularly good quality training data in different continents and biomes. So it needs to be distributed strategically and sampled strategically to represent the whole distribution of these classes. And a standardized taxonomy, because again, these models want to be able to go from different tiers or different classes of land cover and different spatial resolutions. So being able to have these hierarchies that can also be shared across ecosystems and regions, and then have regional heterogeneity, that is a key thing. So we have a global forest class maybe, but if we go with different regions, then we can have those individual nuances. And of course, integration of field data on the ground and expert review. These models, as much as they are powerful and good, we need the experts in the loop. We need the ecologists to come and say if this is working or not. It is not a purely technological question. This is an AI-human collaboration problem to me. We have those architectures, we have the compute resources. It is sitting down with the expert and doing this. So I'm going to leave you with this slide about what is the opportunity, which is an inflection point to me, the challenge, that is the data and the basically stakeholder engagement, and the bottom line that these models are helping us, but we need to also feed them the right data, the right expert analysis to help us get those maths, basically. And with that, I'm happy to take any questions. Thank you.
Thank you so much, Ahmed. That was excellent, and we've got some fantastic questions rolling in as well. As a reminder, if anyone has a question, please do offer them in the Q&A section that's there below. We'll also try to be monitoring the chat that's here. But just to kick things off, Ahmed, our good friend Amy Rosenthal loves this sort of work and questions about different foundational models, pointing out that some are still under development. Like it looks like AI2's new model is Earth System, may be something similar. But one of the questions, or she had a couple of related questions, I think. One, you indicated that Prithvi EO is multispectral, but is that really the only foundational model that is so, that goes beyond RGB? And then second question from Amy, whether or not all GeoFoundation models must be global. And then I'm going to follow up with a question Fred had actually that's related.
So on the Prithvi side, no, that is not the only multispectral data. I tried to select 6 models that had basically representations from the categories that they were in, like a multispectral one, a multi-sensor one, one that goes with the image-to-image translation type of thing. So no, there are other models that are multispectral. I think SkySense is one of them. And there's a wealth of them. There's actually a GitHub repo called Awesome Foundation Models, Geospatial Foundation Models, and it has a list of like 60, 70 models at this time. So yes, there are other models that are only multispectral. That is not the only one. But the number of models that are only RGB are actually larger. So that's the bucket that still dominates the class. And the follow-up question was, I blanked on that. Amy said,
do all GeoFoundation models have to be global?
oh, no. No, the foundation models, geospatial foundation models don't need to be global, but they need to be defined in a region, in a domain, whether it's a geographical domain or a temporal domain, that makes sense to do self-supervised learning. The global one, because it's heterogeneous, you have a lot of data, so it is valuable to do that, but you can do it at finer scale, whether it's a continental level or a country level. But it's just a matter of what is then the utility of the downstream one. We have done this in the regional level too, particularly in Central Africa part, and we see values in doing that. So no, it doesn't need to be global. It needs to be something that is heterogeneous. That should be the domain.
Let me follow up with there's a great conversation in the chat. So thanks you all. And Fred Stoll at WRI has pointed out some really great things. But one question then based on this is, as developing global map to compare countries and ecosystems and such, one of the challenges is that if you regionalize or nationalize the map, you lose that possibility of standardizing across the world. Asking for any suggestions on this regional to global problem.
I think that's where the hierarchical taxonomy is needed, right? So we need to be able to have taxonomies that we can define at the global level, but when we go regional, it feeds into those regional nuances. And that helps you customize it based on what is the definition of a certain cluster. So there needs to be a trade-off there. Yes, we can have only national maps and then do global comparisons. We can have only global maps and make decisions locally because that's what is needed there. I think the solution is to have that hierarchical translation between the two and then build models that can do this hierarchical classification. So a user, a stakeholder, a decision maker can make decisions at the local level, but they can also report nationally and continentally what is their target, for example, meeting some certain policies.
Fantastic. Let me turn the question to another question that's a little bit different, but it's really about what you do with these. And you started out your conversation. So these can obviously be utilized to assess the state of nature. But the question is, how do we understand the level of things like degradation relative to reference conditions? So how would we understand, for example, deforestation in a watershed that increases flood risk and water availability? What's that bridge to intervention?
So some of those applications like degradation and so on, I think we need to go beyond models that are just imagery based. You need to basically bring in like a hydrological modeling into that. And there's a field of geospatial foundation. And that's why I call these Earth observation foundation models, because they are different from weather and climate foundation models. But I think to do something like that you go at a watershed level, you look at the impacts of some practice or some intervention on degradation or lack thereof, you need to integrate other dimensions of the geography, basically. As a faculty of geography, I can tell you, you need those dimensions, basically. And I think that's where integration with other foundation models that look at the weather, look at the hydrology of the ecosystem is needed. And I see some convergence of that in the literature, but it's very early days of that. But it is advancing. We have a field of foundation models that are fully focused on weather and climate, and another track that is on hydrology and self-supervised learning for understanding rivers, for example. We hope to see them converge, and then we have a fully digital representation. I mean, I don't want to use this term, but it relates to some people, the digital twin of like the ecosystem, right? So it can understand all the different dimensions of that, and then you can have a decision-making tool for that.
That's fantastic. I'm going to follow up with Genevieve. Just posted in the chat. People can probably see this great question. Her question starts with the premise that most conservation action depends on regulatory pressures, which requires standards. So how do we standardize this huge number of models that you're talking about, the growing number of models, to ensure that they're accepted from a regulatory standpoint? And how do we deal with what you pointed out, the sort of stochastic nature of results? In ensuring that we can audit this appropriately, particularly in a policy-making or regulatory framework?
To be honest, that is a policy problem than a technology problem. I don't think it is something that purely a technology can solve this. It is going to the policy tables and make a translation from what a model output is to a policy, basically. Because any model is uncertain. It is not like the classical models that we had for land cover were deterministic and didn't have noise. No, those models had too. We saw a lot of good examples here today, right? The issue is we need to be aware when we are making a policy that the data that is fed into, like, let's pick EUDR. Like, we want to look at EUDR and we want to look at if a parcel was deforested before. That data is noisy. So I think we need to solve that at the policy level, that we don't have 100% accurate data anyway. We need to leave some room for accuracy and corrections if the data is not correct. How that can be fed in, it can be the user coming in and, for example, championing, oh, this product that you're using is not correct because of X and Y. We should have mechanisms to go back and validate the model. The interpretability is another key here, basically, to understand how the model made that decision. So iteratively, we improve these models. The iteration over time is another key thing of this, that we can say, oh, the product from 2022 that produced by this institute is going to be our baseline for decision making for the next 10 years. That is not going to make sense, I think. We need to be agile and iterative, which is hard. I understand that. But that's the basically reality of the technology world that we need to connect to the policy. That the data needs to be agile, the decision making needs to update as the new products coming in, and leave some room for uncertainty and error. It is hard to have a map that is highly accurate for a policy that impacts a huge landscape like the whole coffee production around the world, for example, for EUDR. So that would be my suggestion, to work with policies and translate the shortcomings and uncertainties of this technology so the policy can accommodate for those.
That's great. Please do keep the questions coming. We'll try to answer some of these specific ones offline, but let me wrap it up with just one, because there's a number of questions about resources, essentially pointing out that that you need a lot of large compute resources, that a lot of this development is challenging without having access to them. I like the way in the chat one of the questions though was framed. Do you mind commenting very briefly as a conclusion on current bottlenecks going forward, in particular funding needs, and how it is that we can address some of the caveats you mentioned?
Yes. So yes, generating a foundation model, as I said, it needs the heavy compute. It needs institutions coming together. This shouldn't be an individual person or individual institution's decision. As you see, many of these models are actually multi-institution because they put resources together to be able to solve it. And usually those institutions come from different perspectives. One is national, one is a corporate, one is a research. So they bring different perspectives and different resources, and they are able to tackle those large problems of training a foundation model. So I think the collaboration and multi-institution collaboration is key here. Funding specific data and benchmarks is an essential piece here. And benchmarks that are generated for a specific use case by the domain experts of that use case. So it is not like, oh, I'm just going to hire some individuals to annotate things. No, an expert needs to guide them, an expert needs to design how to sample that. So putting some investment in data is key. And to not forget about the last mile, which is whatever we build, it needs to go to decision making, right? So funding pilots, funding or seed funding projects that can work with a stakeholder. I'm going to pick the Kenya Space Agency I work with, enable them, build the capacity that they can consume a map that will come out of this pipeline. And they can also provide feedback to the developer. So it needs to be a fully end-to-end model development to a decision maker use case, so we can build systems and data that can help us make decisions better for the nature.
Excellent. Well, thank you so much, Hamed. Let's all give one more virtual round of applause to Hamed, and a thanks to everyone for joining us. On behalf of Conservation X Labs, the whole team here, on behalf of the Nature Data Lab at One Earth Philanthropies, we're grateful to you, Hamed, for your excellent presentation, and to everyone for joining us. We'll be sure to follow up and post this video online. Please do share it widely. Be in touch, be well, and have a great Monday, everyone.
Thank you all.